For this experiment, you'll need 2 paper cups of any size, a Bunsen burner, two balloons, 1 beaker, and about 500 milliliters of water. You will also need a ring stand. For the first demo, you use an empty paper cup placed on a ring stand over a Bunsen burner. When the Bunsen burner is placed beneath the paper cup will immediately burst into flame. Once it does so, make sure to place the paper cup into a beaker of water. For the next portion of the experiment, place a paper cup filled with water on top of the ring stand and move the Bunsen burner beneath the paper cup. This cup should not light on fire, although there are portions of the cup that do not touch the water and therefore will singe and burn. Notice that the paper cup is not lighting on fire, besides the areas that do not immediately touch the water. For the next portion of the experiment, place a balloon filled with air on the ring stand and move the Bunsen burner beneath it. When the balloon is placed over the Bunsen burner, it immediately pops. Then place a balloon with water on the ring stand over the Bunsen burner. As you can see, despite the high heat of the Bunsen burner, the balloon does not pop. The purpose of this experiment is to view the effect of water's high specific heat. Specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. This is different from heat capacity, which is the amount of heat required to raise the temperature of a given amount of substance by 1 degree Celsius. All substances have their own specific heat, and is given in joules per gram degree Celsius. For example, aluminum has a specific heat of 0.900 joules per gram degree Celsius, while ethanol has a specific heat of 2.46 joules per gram degrees Celsius. However, the 3 specific heats we care about for this demonstration are the specific heat of water, rubber, and paper. These values are 4.184 joules per gram degree Celsius for water, 2.01 joules per gram degree Celsius for rubber, and 1.4 joules per gram degree Celsius for paper. When the paper cup without water is placed over the Bunsen burner, the paper quickly lights on fire. This is because heat energy is transferred from the Bunsen burner up into the paper cup. Since paper has such a low specific heat, the paper soon heats up. As it does so, it nears its ignition temperature, which is the temperature at which the paper will catch fire. At 233 degrees Celsius, the paper catches fire. All the heat energy from the Bunsen burner is transferred directly to the paper cup. However, when water is placed into the paper cup, water absorbs some of the heat energy from the Bunsen burner. Water's high heat capacity allows it to absorb a lot of heat from the Bunsen burner before it increases in temperature. This means that the water keeps the paper from approaching the 233 degrees Celsius ignition point, and it keeps the paper from burning. Igniting paper. The balloon portion of the demonstration was slightly different. Just as with the paper cup, heat energy was transferred from the Bunsen burner into the balloon. However, the balloon did not catch on fire. When the balloon was placed over the Bunsen burner, the air inside it quickly expanded. According to the ideal gas law, PV equals nRT, volume and temperature are directly proportional, meaning that when temperature increases, so does volume. The air inside the balloon increased in temperature very quickly when the balloon was placed over the Bunsen burner. Therefore, the volume also increased, placing pressure onto the balloon. As the air inside the balloon expanded and pushed out, the rubber of the balloon was losing its ability to stay together. The heat weakened the intermolecular forces of the rubber, and this combined with the pressure from the balloon caused the balloon to pop. However, when water was placed in the balloon, the water absorbed the heat energy from the Bunsen burner. This stopped the air inside the balloon from expanding and stopped the rubber from becoming weaker. Again, it was water's high specific heat that allowed it to absorb so much energy from the Bunsen burner without increasing in temperature. So why does water have such a high specific heat? Water contains 3 atoms, 1 oxygen atom with 2 lone pairs on it, and 2 hydrogen atoms, each bonded to the oxygen, to make a bent shape. This shape and bonding pattern of water allows it to have very strong intermolecular forces. Water is polar, with a slightly negative charge on the oxygen and slightly positive charges on both hydrogen atoms. Additionally, water can form a hydrogen bond between the hydrogen of one molecule and the oxygen of another molecule. This allows water to have dispersion forces, dipole-dipole forces, and hydrogen bonding in between all of the molecules. With all 3 of these intermolecular forces, particularly hydrogen bonding, water has very strong attractions between all of its molecules. This means that it requires a lot of energy to break these attractions. This aspect to the intermolecular forces of water means that it can absorb a lot of energy before any of the attractions are broken. This means that water remains a liquid and remains cool. While there isn't much math associated with this experiment, we can look at examples to see the effects of having a large or small specific heat. By assuming that we have 50 grams each of water, the balloon, and of the paper cup, we can look at the direct effects of having a large or small specific heat. First, we'll look at water. By multiplying the amount of water by the specific heat and by the temperature 100 degrees Celsius at the point at which water boils, we see that it takes 20,920 joules of energy to raise water to this point. This is very different from rubber. By multiplying the same amount of rubber by the specific heat and raising it to the same point, 100 degrees Celsius, we see that it takes merely 10,450 joules to raise to the same point. Finally, if we look at paper and multiply 50 grams times the specific heat of paper times 100 degrees Celsius again, we find that it only takes 7,000 joules to raise paper to the same temperature as water. By looking at the percentages, we can see that it takes half as much energy to raise rubber to 100 degrees as to raise water to 100 degrees, and it takes about 30% as much energy to raise paper to 100 degrees as to raise water to the same temperature. Placed over a Bunsen burner. The high specific heat of water reflects this ability. This aspect of water keeps a pool cool on a hot day and it is what stops a paper cup filled with water from bursting into flame, or a balloon with water from popping loudly. This is a very important aspect to water, and is what makes this experiment so useful.